Very much thankful to the organizing committee for having me here today for this international conference on social science, social and scientific awakening in the era of quantum world. So today I will talk about the two-dimensional material for nanoelectronics. Okay, so in coming 45 minutes, I will be briefly covering these things. Actually, I am in between of you and your lunch. So I will try to keep it minimum, whatever I can do. So I will be talking about the introduction of nano and quantum world. I think it is not working on this screen. Okay, this is LED. Fine. And then I will go to the zero-dimensional and two-dimensional material. Then I will talk about the role of two-dimensional material for the field effect transistor. Most of you must have been aware with the this field effect transistor. So basically, when we are talking about the nano and quantum world, so I will start with the nano, and I will give you a brief idea of at the what length scale we are going to talk about. Okay, so everybody is aware with this football. Okay, everybody must have played football. So football size is around 0.22 meter, right? Now, if you increase the size of football to 1 million, 10 million times, then you are seeing the size of the earth, right? And now if you make it smaller 10 million times, then you are having this fullerene, and fullerene is the nanomaterial. So you can imagine the length scale at which we are going to deal with. So nano is something 10 million times smaller what we can see through our naked eye, right? So next few more examples. So we know that this is the human fingernail. It grows 1 nanometer every 5 seconds. Right? No, sorry, 1 nanometer every second. Okay, and this human beard, it grows 5 nanometer in a second. So the growth of beard is relatively faster than the growth of nail. Okay, that's why male people used to trim their beard in every week, right? However, nail you can cut in a month also. Fine. And this is what you are seeing here is the same image of this is the same image of your hair. Okay, so you think that hair is brighter, silky, smooth. It is not like that. If you go to the this nano scale, you will see lots of roughness even in on your hair. Okay, so whatever ad you are seeing, Sunsilk, Dove, those are just for ad. Okay, your hair is not that much smooth. And if we talk about the nano, so here we can see from our naked eye, right? And whatever you are seeing here, this is the silver nano wire resting on the hair. Okay, so again you can see this is much smaller than the thing which you can see from naked eye, right? Now, do you think this nano is something new? No, nano is existing from ancient time, but only thing is that people were not aware with this nano business. Okay, okay, fine. This is the Lycurgus cup kept in the British Museum. Okay, the beauty of this cup is that if you see this cup in a transmitted mode, right? If you put a candle inside this cup and see from the outside, it looks like reddish. Okay, but if you see this same cup in the reflection geometry, by putting the candle outside and see from the outside, it looks like something greenish. Okay, and this magic is because of the nanoparticles. And at that time, the foundry people unintentionally mixed nanoparticle, gold and silver, in this cup. They were not aware of it, but later on, after the scientific development, people got to know that these amazing things comes because of the nanoparticles, that is silver and gold. Okay, and this picture is showing why this in transmitted mode this looks like a red color, and in reflection mode it looks like a greenish. I am not going in that detail. Okay. Another example is, this pottery is having nanoparticles for this coloring. People were using from ancient time, and this is the Damascus sword. Okay, this is having very high strength, very sharp sword. And why this is having very high strength is because of carbon nanotube coated on this sward. Okay, that carbon nanotube grows during the foundry process. So people were not aware of it, but nanomaterial was existing from the ancient time. Okay, when real surge in the nano business started, after the very famous speech of Feynman in his famous talk in ABS March meeting at Caltech in 1950 time, the talk was, there is a plenty of room at bottom, an invitation to enter a new field of physics. Okay, so Feynman was very influential. People took him very seriously. Then he said, the principle of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. Okay, so after his famous speech, people started looking, going to the atomic scale. Okay, now why we are interested in nano? Okay, in general, we used to say that if one of the dimension of a material is in the nano range means 1 nanometer to 100 nanometer, then material used to show unique properties like properties, optical properties, electrical properties, thermal properties. Those things is drastically changed when you compare with its bulk properties. Okay, I will talk about a little bit about these properties. Like, this is the optical properties of gold, which I am going to talk about. Everybody is aware with the color of gold, right? सबने gold का color देखा है, right? So gold is yellow in color. That is the bulk gold. And why bulk gold looks yellow? That is because of the surface plasma resonance. Those who have studied condensed matter physics must have gone through the optical properties of solid. So this is because of the surface plasma resonance. But if you break down this gold, bulk gold, into small nanoparticles, okay, and then this gold looks like this color, red color. This is the maroon color, and this color depends on the size of the particle. Okay, so if you alter the size of the particle, you are going to tune the color of the particle. Okay, so now gold is not looks like a yellow; it is looking like a red. Okay. So you are seeing the change in optical properties when you are going from bulk to the nano. Another thing, you must have seen Virat Kohli having this kind of cream pasted on his face. Okay, this is the sunscreen. I hope you must have used the sunscreen with SPF 30, 45, 60, etc. If you increase the SPF, the cost you have to pay more. Why you use this sunscreen? To protect UV exposure. Right, so generally players they play in a very harsh condition, so they coat this kind of sunscreen on their face. Okay, but you see this is white color. Okay, and on this bottom figure you are seeing half of the face is covered with the sunscreen, which is white in color, half is the transparent, and this transparent is again protecting the face. Okay, with the UV exposure, but you are not seeing any kind of coating, right? This is the beauty of nanoparticles. It is having the ZNO nanoparticles, okay? And ZNO nanoparticle is optically transparent, and that's why you are not seeing any kind of opaqueness on the face, right? So this is again the optical properties of nanoparticles. Another thing is, now if we talk about the electrical properties, when we go from bulk to nano, so graphite, I will talk about this particular material in a little bit more detail, but if you see graphite is a multi-layered system, so each layer is stacked through the weak van der Waals force, what Dr. Vivek was talking about. Okay, now the single layer of this graphite is a graphene, okay, and the bulk is graphite. The electrical conductivity of bulk graphite is 10,000 centimeter square per volt per second, but if you take one layer of this graphite, that is graphene, its electrical conductivity is exceptionally high, which is 1,40,000 centimeters square per volt per second. So you are seeing that the optical properties is tuned. You are seeing that electrical properties are also tuned. And then next is the surface thermal properties. Okay. So there is a famous quote, Chinese idiom, this gold never fears a fire. Okay, it means कि खरा सोना को temperature से डर नहीं लगता, right? So if you see the ornaments are prepared at a very high temperature. 600, 700, 800 degrees Celsius, you can prepare ornaments from the bulk gold. Okay, it doesn't melt, right? But if I break this bulk gold into small nanoparticles, this gold will melt, this gold nanoparticle will melt even at a room temperature. Okay, so it is not always true that gold never fears a fire. It will fear if we reduce the size of the gold nanoparticle. Okay, so why melting point is getting changed? Because now all the atoms are kind of at the surface. Okay, if they are at the surface, little bit of thermal energy will push these atoms to fly away. Okay, that's why gold nanoparticles can melt even at the room temperature. Okay, so now thermal properties are modified. Another last property is the surface property. We know that if we go from the bulk material to the nanomaterial, okay, the volume will remain same, but the surface is going to be changed. Okay, this is the simple example. If we take the 1 meter cube, okay, if I break it into the 8 pieces of 0.5 meter, then surface area is 12 meter square. There it was 6 meter square. If I break it further in 0.25 meter square cube, then surface area is 24 meter square. You are not seeing a very drastic change here in the surface area, but this is the example. If you really go to the nanometer dimension, you see this is the total surface area as a function of the particle radius. Okay, when you are reducing the particle size, and if you are going in this micron size and in nanometer size, you see the surface area is drastically changing. Okay, so when you are in nanometer, the surface area is very high. Okay, and we know that if you have 1 gram of graphene, you can cover a total football ground. Okay, so it means that if you have 1 gram of graphene on a spoon, you have the surface area equivalent to the area of the football ground, where you can play with the different kind of chemistry related to the surface. Okay, so now we have seen different kind of interesting properties which are changing when we are going from the bulk to the nano. Now I will talk about there is a slight difference between the nanomaterial and quantum material. I will take you from nano world to the quantum world. Okay, so basically I told you in the beginning that if one of the dimension of material is from nanometer, 1 nanometer to 100 nanometer, we used to call it as a nanomaterial. But when we can call a material as a quantum material, okay, so this particular cube is showing you a bulk material. There is no any kind of confinement. Means electron is free to move in all the 3 directions. It is not seeing the boundary. Okay. Now, if we reduce this material from one of the direction to the and the electron is restricted to move only in the 2 directions. It is not allowed to move in the z direction. Let's say. Okay. And then this is known as the 2D material. Okay, means electron is free to move in 2 directions but confined from 1 direction. And now if we confine this motion of electron from 2 directions in such a way that electron is free to move only in 1 direction, that is the 1D material. And if we confine the motion of electron from all the 3 directions, then we used to call it as a 0D or quantum dot. Okay. And you may probably ask at what length scale we should reduce the size of the material. Okay, what should be this size of this z axis? Okay, so this size will depend on few of the characteristic length scale, that is the de Broglie wavelength. Okay, so de Broglie wavelength, we know that if particle is moving, a wavelength is associated with the particle, that is lambda equals to h over p, right? Or it should be equals to the Fermi wavelength. If you have the metal, you need to calculate the Fermi wavelength, right? So the length scale varies if you are having the metal, if you are having the semiconductor or different kind of material. Okay. But the interesting thing is that when you are confining the motion of the electron, you are seeing that density of state changing drastically when you are going from bulk material to the 2D material, from 2D to 1D and 0D. Okay. You are seeing in case of 0D very discrete energy state, similar like the atom. Okay. In atoms you have seen discrete energy state. Similar energy state you will see here in case of 0D quantum dots. That's why you see a very interesting properties in case of quantum dots. Okay. So in case of quantum dot, if you have the semiconducting material, the important length scale is the Bohr exciton radius. Okay, the exciton is the quasi-particle. It is loosely pair of electron and hole. So let's say this is the exciton, and if you can calculate the Bohr exciton radius, and the Bohr exciton radius for different material is different. Okay, for semiconducting material you can calculate, because you have in semiconducting material you have this valence band and conduction band. If you have the metal, then you have to calculate the Fermi wavelength, right? So as I told you, when you confine the motion of electron, you actually open the band gap in the material. The discreteness of band changes as a function of the confinement, and then because of this discrete energy bands, you will see the fluorescing nanoparticles. Your particle will now start showing the photoluminescence. If you excite the material with particular wavelength, let's say if I am exciting the material with the UV region, it will start giving the photoluminescence in the visible region. Okay, so UV I am exciting and it is showing the fluorescence of red color, green color, blue color, depending on the particle size, okay, or the what material you are dealing with. Okay, and depending on their optical properties, it can be used for different applications, like for this is for UV photo detector, you can use for bioimaging, you can use for metal ion sensor, you can use for LED. Okay, lots of applications are there for 0D quantum dots, and this is nowadays very promising. Okay, everybody is talking about the quantum computation, quantum cryptography, right? The basic fundamental requirement for any kind of quantum computation or quantum information business, you need entangled source. Okay, so either it should be entangled photon or either it should be entangled electron. We know that for digital electronics you need electrons. So those two electrons, let's say I have two electrons generated from the same parent source. Okay, so these two electrons will be now in entangled states. Their properties are correlated. Okay, so if we know the properties of this one, automatically we know the properties of this one without taking care of this one. Okay, and similarly here we can use quantum dot, we can control this emission of photons from the quantum dot by controlling the electric and magnetic field here, and here we can generate the left and right circularly polarized photon which are entangled with each other. So if we are measuring this particular photon, we are knowing what information is traveling in the second photon line. Okay, so this is very much important. Here quantum dots can be a very strong candidate, okay, for generating the entangled photon and entangled electron. Now I will take you to the another dimension, that is the 2D material. Okay, so rest of the talk will be focused on the 2D material. Okay, so 2D material, I told you, if you confine the motion of the electron from one direction in such a way that electron is free to move only in like a surface. Okay, it is not allowed to free in the z direction. So 2D material basically can have, nowadays people have synthesized, after discovery of graphene, I will tell you something about the graphene. So after discovery of graphene, people have explored lots of 2D material, and now we have a library of 2D material which can show insulator, semiconductor, half metal, semi-metal or superconductor. So whatever the your requirement is, we can solve the 2D material. Okay, you can get from the 2D material. So starting with this graphene, everybody had heard about the graphene because this is a very famous material. This was discovered by Gaim and Novoselov. Okay, these are the two gentlemen. They invented they synthesized this 2D material in their lab in 2004, and Nobel Prize was awarded to these two gentlemen in 2010. Okay, and what is graphene? So I told you, graphite is different layer of graphite is stacked to the weak van der Waals force, and because of this weak van der Waals force we can exfoliate graphene. So this is graphite. Now if I take a single layer of graphite, this is graphene. Okay, and let me assure you that in your life you have many times you have produced graphene. Okay, either you are experimental people or you are theoretical people. Okay, everybody has produced graphene in their life because you have used pencil. Okay, all of you must have used the pencil. Pencil is made up of graphite, okay? And when you are writing with the pencil, you are producing graphene, okay? You can take a water-soluble paper, you can scratch on the water-soluble paper and dissolve this paper in a water. Now you will have graphene floating on the water, okay? So everybody has produced graphene in their life. Why graphene is important? Okay, see, graphene is optically transparent. Okay. So single layer of graphene is optically transparent, and you can see that this is also flexible. If I transfer graphene on a polymer substrate which is optically transparent, then we will have the flexible electronics, transparent flexible electronics. Okay, and it is mechanically very strong. You must have used the cling film in your kitchen. So if I have thickness equivalent to the cling film, then you see it can hold even an elephant. So this is mechanically strong because of the in-plane covalent bonding. Okay, so in plane there is a sigma bond which makes graphene very strong, right? And this setup is in this particular slide I want to show you. This is the setup in our lab. We are using it for producing graphene. You see, this patch is of graphene on silicon oxide, and you can see this is graphene on quartz substrate or glass substrate. You know, glass is optically transparent, and when I transfer the optically transparent graphene on glass, now I have conducting transparent substrate. Okay, so this is the beauty of graphene. And you can easily confirm the growth of graphene by using the very simple experiment, that is the Raman spectroscopy. If you have the single layer graphene, you will see that very sharp 2D band, okay, a double Raman resonance peak here at 2D, and this FWHM full width at half maxima of this 2D peak is around 25 to 30 centimeter inverse if you have the graphene, single layer graphene. Okay, and one more thing, if you have single layer graphene, the intensity ratio of 2D and G, 2D will be more than 2 times than the G. Okay, this shows the quality of the graphene which we are producing in the lab. Now I am going to going for another 2D material. Okay, and why my focus is for another 2D material wherever graphene is very famous 2D material. Okay, the problem with graphene is that it is a zero band gap material. Okay, so there is no band gap. But we know that we have seen this era. Maybe young people must may not have seen this particular era, but I have seen this telephone. Okay, this telephone, now this is reduced, this one, now we have pocket mobile, and more importantly, we have computer in our pocket, right? This is smartphone are working like a computer. Okay, so whatever we can do on computer, now we are able to perform those things in a pocket mobile. And why we are able to do? Because we have miniaturized all the electronic components. Okay, and when you are miniaturizing the electronic component, so the heart of electronic component is field effect transistor. If you see any IC, okay, so IC, the basic component of IC is the field effect transistor. Okay, and the field effect transistor is made up of silicon. The problem with silicon is that if you reduce the size of the silicon, after a certain limit you can't reduce its size. Okay, because there will be free dangling bond and there will be scattering of electrons. Okay, and the silicon will not be stable at that scale. That's why we need 2D material which is stable and it should be semiconducting. Okay, silicon is semiconducting. You must have gone through the field effect transistor. In field effect transistor, there is a source, drain, gate, and the substrate. In the channel, you need a semiconducting material. That's why we need a 2D material which is semiconducting in nature, right? So this transition metal dichalcogenide serves our purpose. Basically, transition metal dichalcogenide is having, this is again different layer of transition metal dichalcogenide is connected through weak van der Waals force. Okay, similar like a graphite. And because of this weak van der Waals force, we can exfoliate this material in a single layer. And a single layer of transition metal dichalcogenide is a kind of having 3 sub-layers, where in these 3 sub-layers, the central layer is of transition metal which is sandwiched between the 2 chalcogen layers. So this is not actual 2D material. If we take the single layer of TMD, it is a kind of quasi 2D material, okay, because there are 3 layers, okay. And this transition metal dichalcogenide, generally there are 2 polymorphs of transition metal dichalcogenide. One is the 2S, which is semiconducting in nature, that is trigonal prismatic, and another one is the trigonal anti-prismatic. You just rotate from the center. So this is the trigonal anti-prismatic. And if you see this polymorph from the top, it looks like a hexagon, similar like a graphene. But this is not a graphene, because alternate atoms you are seeing, in case of graphene, every atoms are carbon. Here one atom is transition metal, another is the chalcogen, right? It is different from the graphene. And if you see the 1D phase of transition metal dichalcogenide, it looks like a 2 interpenetrating hexagon, okay? And 1D phase is metallic and 2S phase is semiconducting. Our interest is in semiconducting, okay, because we want to develop 2D field effect transistor, okay. So one interesting fact about transition metal dichalcogenide is that if you reduce this number of layers, means if you are going from multi-layer to the mono-layer, this material, this is the semiconducting, this is indirect band gap semiconductor, okay. Now if you go to the mono-layer, this becomes direct band gap material, okay. And because of this direct band gap material, monolayer of transition metal dichalcogenide gives a very unique optical properties, because now excitonic properties are modified. Just to check that optical properties, first we synthesize 2D WS2, where W is the transition metal and sulfur is the chalcogen. This schematic is showing the growth process. Okay, we use the atmospheric pressure CVD technique for the growth of WS2. Okay, this triangle which you are seeing here is a WS2. Lateral size is around 40 micrometer, and when we perform the atomic force microscopy, we find a height difference of 1 nanometer between the substrate and the crystal. It means this is the monolayer WS2. Okay. And then we were interested in seeing the optical properties. As I told you, this material goes from indirect band gap to direct band gap semiconductor. So we checked the optical properties of WS2 crystal, and we observed that monolayer of WS2 gives a very strong red luminescence when we excited this material with the green light. Okay, and this comes because of this confirms that material goes from indirect band gap to the direct band gap, right? Then our primary interest was to develop 2D field effect transistor. Means we wanted to use this 2D material as a channel. As a channel, you see here, this is the schematic of bottom gated field effect transistor. Okay. In your theory classes, you must have gone through the top gated field effect transistor. Okay, where your gate is at the top. Now we are using this as this highly doped silicon as a gate. Okay, so we will apply the potential at source, drain, and the bottom gate, and here is the channel material is a 2D WS2. Okay, it was fabricated using the photolithography process. Okay, and then we check the output and transfer characteristics of this WS2 crystal, and you can clearly see that it is showing the linear region and saturation region similar like the general MOSFET which we are aware with, right? And in the transfer characteristics, you can see if we plot the drain to source current with the function of backgated voltage, you can see there is a very sharp on-off current ratio which is of the order of 10 to the power 6. Okay, so for any electronic device, we know that the switching is very important. Okay, and the switching on-off ratio should be very high. Otherwise, there will be the leakage current, and your electronic component will never be go to the off state, right? That's why it is very much important. This on-off ratio should be very high, and luckily for this material, we got it is of the order of 10 to the power 6. It means the synthesized 2D material WS2 can be easily used for the 2D field effect transistor, right? And the field effect mobility was calculated from this transfer characteristics curve, and we got it around 6 centimeter square per volt per second, which is relatively less. That's why we again synthesized another 2D material, that is WSE2. So transition metal is same, but now we change the chalcogen. okay, which is selenium now. In this case, again we had the triangular morphology, and you see height difference of 0.9 nanometer around. In AFM clearly confirms that this is again a monolayer WS2, and we again fabricated field effect transistor of this WSC2 crystal, and this is now you see these are the chromium gold contact pad on this WSC2 crystal. This WSC2 crystal again around 30-40 micron, and the channel width, this channel width is 1 micrometer, means 100 nanometer, approximately 100 nanometer channel width is there. And then we check again the electrical properties of this 2D field effect transistor. Now in this case we got this field effect mobility was doubled. In first case it was 6 centimeter square per volt per second, and here it is 13 centimeter square per volt per second. So this is much better than the WS2. So we found that WSC2 is better candidate for 2D field effect transistor than the WS2, right? And then again you can see this linear region, saturation region in case of output characteristics, and in transfer characteristics you see a very high on-off again. So this is a good candidate for 2D field effect transistor. In our lab we are growing some other 2D materials also, like pristine and doped TMDs, right, to modify its optical and electrical properties. So we are working for different 2D materials like VS2 pristine, MOS2 pristine, and VS2 pristine, and molybdenum doped and NB doped VS2 samples, just to check their modified optical and electrical properties. Okay, so at the end, let me tell you, all these works, the hard efforts of myself and my PhD students. And you see, this guy is the instrumental in doing these works, Mr. Ankit, and our collaborator, Professor Saptarshi Das, who is from Penn State, University of Penn State. So we are collaborating with him for some of the work. Okay, and at the end, for financial support, I will acknowledge DST, okay, who gave the financial support, and my institution, IIT Roper, right? So thank you.
So this talk is open for question and answers.